I actually started recording. And you started it, okay. So yeah, that's the plan at the moment. But depending on how it goes, I might actually try to release the final exam a bit early, and then close it a bit early as well, so that you will have more time to travel somewhere for the winter or whatnot. But that's the plan at the moment. We'll never actually push it back to the early. Might actually pull it back, pull it forward. All right. That's it. Any questions on this part of logistics, in particular involving the final exam? No? And as was announced, the grading criteria exactly as written down on the syllabus. Yes.
Yeah. How long is the exam going to be?
It's going to be about twice as long as the usual weekly. That's the goal. But of course, the difficulty of individual question is pretty much up to you. So some of you might think that it's as short as any individual weekly quiz. Some others might feel that that's like 10 times longer than weekly quiz. But because you've been taking all these weekly quizzes and coming to the lectures, hopefully it's going to be reasonably easy. All right, that's it. So what have we learned? What did we learn last week? We learned how to conditional language model, right? So how to extend what we have learned so far into building some system that is actually useful, that is given some question that could vary over the source sentence. Now, tell us the answer. Could be answers in the question, in the case of the question answering, in the case of machine translation, that's going to be translated. Now, today we are actually go back into a bit more conceptual and mathematical ideas. And in particular, we're going to look into the idea of the matrix factorization. Due to the, yes.
I have a question. Yeah. Something you said transformers cannot even count words, but counting is harder and linear. They should be.
No, so unfortunately transformers can't really count. It can count up to the number of the layers you have. Now, of course, there is a normalization constant in the softmax that is the summation over n. That's true, except that it's just linear operation. However many linear operations you have, that you can always collapse them into a single linear operation. So that doesn't really count as the order n. So the computational complexity for each location, so they take any location within the input, right? And then you look at the target side, and then you can now count the number of the nonlinear functions that has been applied. And then that's unfortunately constant with respect to the length or the size of the input in the case of the transformer. In the case of recurrent neural network, that's O n, okay? So that's linear. If you add recurrent neural net together with the attention mechanism, then you can actually grow it all the way to the quadratic, so O n squared. However, that's about it. Going beyond that with this neural net is actually non-trivial at all. And then that's the unfortunate discrepancy between the neural nets that we use in practice versus the theoretical, let's say, limitation that is imposed by the neural network. In theory, if you allow the neural net to be able to compute as much as you want, regardless of the size of the input, then these neural nets, in particular the recurrent neural nets, as well as the transformers that we have built for slightly modified version, are all so-called Turing complete. You can actually compute whatever you can with the Turing machine. And then that's like pretty much the best we can do when it comes to computation. Unfortunately, that's not really realistic. That's not really realistic because we don't know how to make our neural net perform an arbitrary number of steps given any. Unfortunately, we don't know how to do it. So that's kind of where the gap actually is. Because otherwise, we would just ditch all those computers or the softwares and then just train the neural net to solve everything. But unfortunately, any other questions along the line? That's a pretty important point, actually. Because at the end of the day, it's really difficult. One thing that is really difficult to tell in advance of using any of these machine learning algorithms for solving the problem that you have is that whether it's going to be able to solve the problem. And then the saddest thing is that we have to train a model and test it in order to tell whether the problem is going to be solved and to which degree. But then, what is the minimal kind of, let's say, guidance we can have? One of them is what kind of, let's say, computational complexity you would expect your problem or the solution to your problem to have, and whether your neural net is able to do so, perform the computation that amounts to the kind of worst case or the average case minimal computational complexity you expect your solution to have. And this is just one of those, let's say, things that you can take into account. All right. Any other questions before we go back into a bit more boring conceptual, let's say, ideas? Okay. In the case of matrix factorization, the very good thing is that you have all learned what matrix factorization is, assuming that you have taken all those courses that were in the preliminary course list in the syllabus. Some of the matrix factorization algorithms include principal component analysis. You can also use a singular value decompositions to do the same thing as a principal component analysis. You may have heard about the non-negative matrix factorization. And then if you have taken the linear algebra course and then taken it really carefully, you know that there are many different ways to decompose a matrix into 2 or 3 matrices, or the product of the 2 or 3 matrices, right? So for instance, the LU decomposition, QR decomposition, all those things are part of the matrix factorization. Matrix factorization has a very special role in general machine learning, because at the end of the day, the data we have, we can always put it into a form of a matrix. Each row corresponds to each example in your data set. And then each column corresponds to the value that you assign to one of the features of the data point. So in other words, if you have data, we can always massage it in a way that is going to now look like a matrix. Now, I'm not saying that that's the only way to represent it, but the matrix is one way that allows us to represent any kind of data really, really well. Then once we do so, we can use all those techniques and algorithms coming out of linear algebra in order to do what we want to do with the matrix. And then the nice thing is that this actually doesn't matter. This doesn't care whether we're working on a supervised learning or unsupervised learning. Because in the case of supervised learning, you can just expect to have few columns of this matrix used to represent the target or the label. It's a pretty generic, let's say, way to view what data is. And in the context of the natural language processing, it turned out that the matrix factorization, or the view of the matrix view of the data, is pretty much perfect. A perfect way to, let's say, encode or to reflect the distributional hypothesis that we've been talking about over and over. So let's think about how we do that. So distributional hypothesis. So what was the key idea behind the distributional hypothesis? That's really interesting. All right. Okay. That's great. So what was the core idea behind the distributional hypothesis? The meaning of a word. Meaning of a word is determined by other words that appear together. Right? That's the idea behind the distributional hypothesis. So if you look at the words in the context in which the target word appears, we can now tell what the target word is. And that kind of makes sense, right? So that actually was one of the motivations behind our idea of building a mask language model. We can often determine what a missing word is if you look at the entire context in which the word appears. So then, in this particular case, if I consider a one-word W, let's say I'm going to look at the word W, whatever the word is, right? Let's say I'm going to look at a word cat. Then what would be a reasonable set of features I can use to represent this W? I can probably look at which words does W appear together with. And then perhaps I can say that they're within some distance. So I'm going to go through the corpus, large data set I have collected. And I'm going to look at every time this word appears. And then given that word, I'm going to look at a small window surrounding that W and then see which of the words appear together with this W. And then perhaps I could even imagine that the distance from which that particular word appears from W matters. So we can actually think about many different features that allows us to encode this context in which the word W appears. Now, in this particular case, we're going to simply say that we're going to just look at which word actually appears within some small window. And let me use a phi of W to indicate this is a feature vector of W. Then I'll say phi of W, ith dimension of the phi of W is the count of the word I, appearing in the context of W. So just like what I said, so I go through all possible occurrences of W. For each one of them, I look at sums, let's say small window surrounding it. It could very well be the entire sentence, it's fine. And then within that, I try to see how often the word I appears, right? And then I can just call it word I because we all know that the words are really nothing but just indices by which we can just find the corresponding word in our dictionary. So this phi of W is going to be a very large vector, right? How large is it? It's as large as the number of unique words in the vocabulary. And then for each dimension, I try to look at how often that particular word co-occurs together with the target word W. So this vector can be thought of as the co-occurrence vector. Or the co-occurrence statistics or vector of W. And then now, once we build this kind of co-occurrence vector for each and every word we have in the vocabulary, we can now build something called the co-occurrence matrix. And then I'll call it A. And then this A is going to be the stack of all these co-occurrence vectors or the statistics. So we're going to have the transpose here because we often work with the commas. The size is going to be the number of unique words in the vocabulary by D, where D is going to be, well, sorry about that. It's going to be the size of vocabulary. So we're trying to look at for every word in the vocabulary, which of the words in the vocabulary co-occur together and how often. So this is going to be very large and often sparse because not every word appears together. So co-occurs together with all the other words. It's often very sparse. Yes?
How are you choosing the size of the window?
Oh, it's up to you. It's up to you. It's up to you. And then, so why do I say it's up to you is that the size of the window, or as well as all the other hyperparameters that we're going to talk about, are the ways for you to determine or to decide what you mean by the context. So distributional hypothesis tells us a very loose kind of hypothesis that says that, okay, we need to look at what other linguistic units appear together in order to tell the meaning behind some linguistic unit that doesn't even have to be a word. It can very well be a letters, phrases, or even sentences or paragraphs, right? So in the case of the sentences, you look at what other sentences appear together, then you can get the sense of the meaning of the sentence. Now, but then what is the context, right? The context is not really like let's say the single thing that is defined, but that's going to differ from one problem to another, one language to another, and from one user to another user. So in this particular case, you can imagine that in the case of English, it makes sense to look at about, let's say, 10-word window, then that often gives you this sense. But it's going to be heavily application as well as a language dependent. But let's say we're going to build this co-occurrence matrix. Not too difficult. I mean, it's going to be very sparse, right? That's the one thing for sure. Then it's very large as well, right? So if I have a million word vocabulary, I'm now going to have million squared number of entries. So it's not too surprising that this is going to be a very sparse matrix. Now, what we are going to do is we're going to now, use a principal component analysis here. So why do we want to do that? Because of the sparsity. One thing we know is that it's not going to really, these features are not going to be perfect. So we want to use these features as if those features are telling us about the meaning of the word. And then what can we do once we have a vectorized, let's say, feature of the words? We can always check the similarity by looking at the dot product or cosine similarity or whatnot. That's what we've been doing. Except that because of the sparsity, we're going to get that almost everything is orthogonal with each other, meaning that none of them is really similar with each other. So what we do is we're going to try to reduce the dimensionality and then remove many of the dimensions that are irrelevant and then leave only a very important principal dimensions. Now, if you recall from the principal component analysis, the first thing you need to do is to compute the mean and subtract that mean from every row in the matrix. So compute and subtract the mean vector or the average vector. Where the mean vector mu is going to be 1 over the size of the vocabulary, sum I goes from 1 to the size of vocabulary, b of w. So we just go through each and every row, just essentially sum them and then divide it by the number of the rows. And then what is this? This you can think of this as the kind of average co-occurrence statistic. If you don't know which word we are talking about, how likely would another word co-occur together with this word that you don't know? That's what this average tells us. Yes.
Does a word co-occur with itself? Like
the word can co-occur with itself.
I mean, would you count it? Like would it always count 1 for itself, or would it only be?
You actually don't have to. So the self co-occurrence is not necessary, but the thing is that it's going to be just diagonal, right? And then that is going to be the exactly same number for every number. So in fact, it's going to be subsumed by the mean vector. But then the thing is, can that word appear together in the window, right? Twice, then you should count. Right? So that's the thing that is interesting is that the words do appear multiple times, even within the single, let's say, single window. And mostly those are often functional words, but still. Any other questions? So this mean is kind of, let's say, our idea of if I didn't know which word I was talking about, would I know, what would be my best guess about which other word is going to co-occur together? So what would be some of the guess we can make? Though, we know that they are going to co-occur with almost every other word, with a very high chance. On the other hand, let's say some proper names, they are not really going to co-occur with any particular words better than any other particular words. So that's kind of, let's say, mean we have. And then in principal component analysis, one of the most important thing is to subtract the mean. Almost everyone makes a mistake when they have to implement it themselves. And then we're going to center all these rows. So we just subtract them. Right? And then we're going to call this a centered co-occurrence matrix. Oh, by the way, you don't have to like memorize these names or anything like that. I'm just making up these names as I teach, so no one calls it like that as far as I can tell. So don't worry too much about it. And then now what we want to do is to factor this centered co-occurrence matrix, A tilde, into the product of two matrices. And then those two matrices are going to be U and V. U is going to be the matrix, real valued matrix of size, the vocabulary size by D. And then V is going to be again the same kind of matrix of size, the size of the vocabulary by D. Then here, D is going to be almost always much smaller than the size of the vocabulary. Which kind of makes sense here. The size of vocabulary is going to be in the order of the hundreds of thousands, if not millions, if not tens of millions. And then what these U and V refers to are the left and right matrices, or another way to you can imagine is that the U is going to be our word embedding matrix, and then V is going to be our context embedding matrix. We'll see what why that is so. Now, in the case of the principal component analysis, there are many different ways by which you can arrive at the exactly same formulation. Often, if you learn about the principal component analysis from linear algebra course, what you learn is that there is a way for you to orthogonalize your matrix or diagonalize your matrix. If you learn principal component analysis from the Intro to Statistics course, then you learn that there is a way for you to estimate the directions that have the maximal variance. Now, in our case, in particular in machine learning, the most preferred, or I think that the most intuitive way to derive or think about principal component analysis is to find the orthogonal factorization that minimizes the reconstruction method. That is, the goal of principal component analysis is to find the matrix U and V, and then they're going to be orthogonal matrices, but especially in machine learning, we actually don't care. We don't really care whether they're orthogonal or not. But what we care about is that if we look at the product of these two matrices, the product of matrix has to be very similar to the centered co-occurrence matrix A tilde. And let's just look at this objective function. This objective function can be rewritten as going through each and every element in A tilde. So we're going to go through each and every row and each and every column. That's going to be INJ. And we look at the co-occurrence count of the ith word and the jth. So this tells us how many times the ith word appear together with the jth word in the context that has been defined. Minus, we're going to take the ith row from U matrix and then compute the dot product against the jth row from the V matrix. So we take the ith row from U matrix, jth row from the V matrix, and then we compute the dot product. And we sum the square of this difference. So these two are the same thing. And then this is what I meant by the, first of all, reconstruction. So we started with the oops, I forgot to actually put the tilde there. So tilde to mean that this is centered as well. So we subtracted the mean. So what we're trying to do is that we're trying to see the deviation in the count, co-occurrence count away from the mean, right? Something that context actually matters. Right? So what is the mean co-occurrence count? That is a count that we can guess without the context. So we're only going to consider the deviation of this count away from the expectation, right? Expectation that we can guess without looking at the actual context. And then what we're saying is that this value, this count, has to be reconstructed as the dot product between the word embedding. So this is a vector, right? Word embedding and the context embedding. So if I look at the ith word, so I have some vector that tells me about the ith word. And then if I have a vector that tells me about the jth word in the context, then by looking at the dot product of that, I should be able to guess or reconstruct what the count is going to minus, of course, the actual mean that I can guess without looking at the context. So this is why we want this kind of reconstruction loss. And then the orthogonalization doesn't really tell us this story, right? So in other words, we start from a very large sparse matrix called statistics, and we try to factor it into a product of two matrices. And these two matrices are much denser, and then does not jointly have a much fewer entries than a tilde itself. And how we get these numbers is to ensuring that when we take a word vector from U and then corresponding context vector from V and then compute the dot product, that value has to be a good reconstruction of the correct co-occurrence count or the co-occurrence statistics. So that's the reason why we often call U as the word embedding. Well, I probably should say that the I often call them, and then the V as the context embedding. And if you recall from earlier on, calling it word embedding and context embedding is not that surprising in some sense, right? What did we have? We had the embedding of the input, right? And then we had the class embedding as well earlier, when we build the text classifier based on the continuous backover. And then you can imagine that this is exactly doing the same thing, except that you are not trying to predict or to compute the probability to which the input belongs, but rather this combination, this dot product, has to correspond to the co-occurrence count of I and J. Now, just one caveat here is that if the D is not so much smaller than size of the vocabulary, let's say D is very large, as large as the size of the vocabulary, although it doesn't even have to be, then there are many trivial solutions, such as simply setting U to be identity and the V to be a tilde, and that's going to solve the problem perfectly. That's the reason why in the case of a principal company analysis, D is said to be very, very small. So what that means is that we start, oh yes.
I want to know, like, is it just a hypothesis? We consider U to be the word embedding matrix and V to be the context embedding, or is it just going to be the case? Because I don't see it's necessary to interpret it as word embedding in context.
Yeah, we'll get to that. So the question is that where does the semantics behind U and V come from? So it feels quite somewhat, let's say, somewhat arbitrary. Now, in particular, if you look at the U, perhaps that's actually pretty natural because every row does correspond to each of the words in the vocabulary. And then we said that the row is a feature vector of the particular word. Now, the confusion comes from the fact that we looked at the co-occurrence statistics between the words only, pair of words. So in fact, this is a symmetric matrix. We could very well just transpose it, then the context and the words, their role flips. Now, depending on the assuming that we have chosen a reasonable, let's say, definition of the context. That's why the word and context embedding seem pretty symmetric, and then we can flip it. But then there was absolutely no reason why the columns had to correspond to the words. Why do we need to say that we want to look at which words appear together with the target word W? There's in fact absolutely no reason to do so. Right? What if I wanted to see whether each word co-occurred with bigrams? So I'm going to look at for each word, and then I look at where they appear in the corpus. I look at the context. Then instead of looking at which other words appear in this context, but I'm going to look at which two-word phrases appear in this context. I might want to look at which trigrams appear together. Maybe I want to just look at all possible n-grams that you can imagine that appear together with this particular word. Then suddenly this A tilde or A so it's not really a square symmetric matrix, but it's just a rectangular matrix where we can have exponentially many columns as with respect to the n, that the length of the phrase is that we consider. So that's the extension to n-grams. In fact, this is exactly what we're going to talk about. So let's try to extend it to n-gram and then see what is kind of, let's say, what are the consequences that we get. So instead of building the original, let's say, co-occurrence matrix from above had as many rows as there are words in the vocabulary, and then as many columns as there are words in the vocabulary. But it doesn't have to be like that. Right? It doesn't have to be like that. Sometimes we want that to happen, but maybe not always. What if I make A so that there will be still as many rows as there are in words in the vocabulary, but now I'm going to make it so large so that there are as many columns as there are n-grams. There are as many columns as all possible n-grams. That's going there, and then there are going to be n to the power of the size of the vocabulary manual. But how to construct this A matrix is exactly identical to how we would construct this A matrix above. For each of the word, we go through our training set or the data set. We look at where it appears, and then based on our definition of the context, we're going to look at which of the n-grams appear there. Then we're going to just count them. So we can this is a very straightforward process, although it is becoming increasingly more difficult to do. The matrix is just growing up so fast. And then perhaps that's the reason why we want to factor this matrix A into the product of two matrices, and then look at the word embeddings and then context embeddings that are much more dense. Because as A becomes larger, it's bound to become sparser because the size of the data set doesn't really change. All right.
It's mod V to the power n.
Sorry?
It's V to the power n.
Yeah, that's true. Yeah, you're right. Sorry about that. It should be B to the power of n. So then, let's just go back to how we derived the things. Now, what we want is that we want to factor this A or the A tilde, right? Because we're going to have a mu that is going to be again the average feature vector. So average co-occurrence statistics. So A tilde is going to be A tilde minus mu from every row. And then let's see. So we want to minimize the Frobenius norm of the difference between A tilde and U times V transpose. Now, what are the sizes of U and V here? Size of the U is as usual, size of the vocabulary by V. But then the size of V is going to be gigantic. It's going to be V to the power of n by V. So even when we try to factor it, it can become a bit problematic. A lot of the rows in the V are never going to be, let's say, anything other than 0. In other words, this matrix is extremely impractical. So how are we going to avoid this issue? It turned out that we already have learned how to tackle this issue. So that is, we want to start from this A matrix, and we want to do matrix factorization into two matrices, U and V transpose. And unfortunately, this B matrix turned out to be too large for us to handle. And we know how to handle it. That has been, let's say, the 2/3 of this course so far. So I'll just go through two possible ways we can handle, and then I'm going to let you actually think about how we can handle it. The first one is continuous backover. And then we have learned about continuous backover over and over, so you should be very familiar by now. And in this particular case, what we are saying is that we're going to approximate it. So we're going to look at the one particular entry in this gigantic matrix B. So Vij, we say Vij is not a scalar that is independent of all the other entries in the V matrix, but it's going to be the sum of V prime ij1 plus V prime ij2 plus all the way to V prime ijn, where J is n. So the J, what is this J? J refers to one particular n-gram, right? In this case. So we can rewrite this J as a sequence of these n indices. Because J is just an n-gram, so we need that to index the J. Then what we say is that if we are going to have now n many V prime matrices, and then each and every one of these is going to be only the size of the vocabulary by D matrix. But then we just sum them in order to get the entry for this Vij. So let's write it here. So V prime matrix, we're going to have the 1 all the way to V prime n. And then each one of these is going to be V by D. So what we are saying is that the value of the ith dimension of the J n-gram can be rewritten as the sum of the ith dimension of the J1. So the first word of this n-gram from this V prime matrix, and then the ith dimension of the J2, the second word in this n-gram from this V prime matrix. I'm sorry, there's only one V prime matrix. And then all the way until taking the ith dimension from the nth word in this n-gram matrix. So we're effectively saying that instead of using b to the power of n times d many numbers to represent this large V matrix, we are instead going to use b by d, b times d many numbers, but by composing them as a summation, we're going to represent all those many numbers. So that's, and then why is it backward? Because once we do use this summation, you can always change the order. So the order information has been ignored. So we're looking at now the backward. So each jth n-gram is considered, we use the backwards representation to get what that actually means. And with this in our mind,
J is a vector.
no, J is a sequence. J is an n-gram. So then, now from here, now let's go back to this principal component analysis or the minimum reconstruction error-based matrix factorization. We solve the problem of U and B, but it's not B anymore. It's B prime. So we're going to use B prime instead of B. A tilde minus U V transpose squared for B. If you rewrite this part again, then what we end up with is we're going to look at the summation that goes from I1 to V, summation where J goes from 1 to the V to the power of N, and then we're going to look at Phi Wij. So we're now J does not refer to a word in the vocabulary. It refers to a n-gram minus summation over now n prime going from 1 to n, because we are using a continuous backover. It's going to be U, Ui transpose V prime J n prime. Now where does this term come from? That comes from this. So instead of using Vij as it is, we're going to use the sum of the unigram or the word level context representation. So in this case, it becomes quite clear why we call this word embedding, why we call this in particular the whole B part, the context embedding. So looking at this, sorry, square here. Looking at this, we can now immediately see what would be yet another way to efficiently parameterize this very large B matrix. What would that be? We would use neural network, right? We're going to use neural network. So we're going to continue from here. What we're going to do is now going beyond backward. That is, we're going to gain the same thing, sum from 1 to n, j from 1 e to the power of n. Now we have the co-occurrence statistics, right? Co-occurrence statistics, all fine. Minus ui transpose. And then some neural network that has its own parameters that's going to take as input the j, right? And what was j? J is the n-gram. And in fact, I'm going to write it further. Saying that the minus ui transpose f theta of j, and I'm going to, oops, tilde, I was missing tilde here, plus mu j. So because you had the phi tilde wi j was phi wi j minus mu j, right? So this is a centering part. We can just plug that back in here. Right? Now, what is this? If you recall from the intro to machine learning or the intro to data science course, this is regression. This is a neural net-based regression that's going to take as input an n-gram. And then it doesn't even have to be fixed n anymore because we know how to build a neural net that handles a variable length input. We can use a recurrent neural network, we can use a transformers, whatever you want. And then this neural net is going to summarize this into a single vector. And then this UI actually works now as a class embedding. So given the context, whatever the context is, now how often would that context appear together with this target word? And then we have the bias as well. And then the target is this count. Target is this count. And if you think about it, let's go back to the mask language model bird. What would be this J? This J is going to be a sentence with the ith word missing, this UI missing. And then what we do is we use transformer to encode this sentence with some of the mask or the word that is this ith word missing and then masked out, get the representation, and we're trying to see how often this one would appear in the context. If its value is high, that just means that this point is very likely to appear there. If this is close to 0, it would not appear. And then this is a part where it's just a word frequency. So even without looking at the context, how often would this I appear or the J appear? Depending on how you actually parameterize, should probably be I, but all the same. The J and I are same. So what that means is that this matrix factorization, we studied this today, unlike what we've done so far in this semester, we've gone the other way around. Is that we start with the matrix factorization, a matrix that actually tells us what is this pattern that we can extract from this document that tells us about the semantics or the meanings of all these linguistic units. So what we do is we try to look at each and every word or the linguistic unit for which we want to get the representation out of. And then we look at the co-occurrence statistics against another type of linguistic unit. It could be same, that was the very first one, where we look at whether each word, how often each word co-occurs with each other, another word. But what we are seeing here is that that can be very flexible. We can have a very different linguistic unit on the rows, very different linguistic units on the column. And they can be as complicated as just the entire document if you wanted to. And then now what we realize is that this is really nice, this PCA or the minimum reconstruction error approach is really nice, except that depending on the choice of the linguistic units and the choice of the context to form this A matrix can be gigantic. And then thereby U and B matrix, so the left and right matrices can be really, really lovely. What can we do? It turned out what we can do is to parameterize those U and or V matrices in a way that is parameter efficient. Instead of having the number of the parameters growing exponentially with respect to certain choice of linguistic units, but we are going to use a much more efficient parameterization. And then these two parameterization we just looked at are the ones that we have learned over the entire semester so far. The first one was the continuous backward. Very simple. We say that any large chunk of the linguistic unit is just a sum of a smaller unit, such as words. Now, but we know that there are some issues with that approach, right? We learned the issues. First, it's just linear, so you cannot really capture all those higher order interactions. Second, is that it's really difficult to encode a very precise meaning of the locations. So instead, we can decide to use a more sophisticated neural network, such as that here. And that's going to encode whatever the input, the context is, into a single vector of whatever is corresponding. And then what that means is that here as well, we've been talking about U as the word embedding. It doesn't even have to be a word embedding. You can imagine that if you're trying to look at the n-gram by n-gram A matrix, sentence by sentence A matrix, paragraph by paragraph A matrix, and all those things are all possible. Now, just one last thing. So in the case of the continuous backward, pretty clear, we are saving exponentially in terms of the number of parameters. Now, in the case of F, when we build a neural network, that's a bit difficult to tell. However, one thing for sure is that when we build the neural network, eventually we fix the number of the parameters. We have a finite number of parameters. And then the finite number is often not a function of the dimensionality or the size of the input. So that's the reason why we almost always get some kind of, let's say, save. It's better than continuous backward because it can now have it can be a very non-linear function that captures all those high order interactions among the smaller units that constitute this input, whatever the linguistic unit is, the sentence, paragraph, document, so on. All right, perfect timing. So we're going to take 5 minutes break. We'll come back at 5:55. And we're going to look at yet another perspective into this matrix factorization in order for us to prepare, in order to prepare us for the next week's lecture. 5 minutes. All right, welcome back, welcome back. So we have talked about matrix factorization, and then this term, matrix factorization, tells us that there is some static element that is matrix. Somebody gave us this matrix, and our job is to factor it into some smaller matrices. In particular case, we've looked at how to split this one large A matrix into a product of 2 matrices. And we talked about the case where even then one of those matrices or both of them might be too large, in which case we're going to use continuous backward or some kind of clever trick in order to reduce the number of parameters dramatically further so that we can actually try to use this idea of matrix factorization. But then it's a very interesting thing about machine learning is that we tend to find the different stories that go together with the same approach. And then one particular story that is relevant for today as well as the next week is a generative story. what do I mean by the generative story? So instead of think of it as someone gave us this co-occurrence statistics A. So let's not think about it. Let's say no one gave us this A. And then our job is to think of how A happened. How was A generated? Let's imagine a one particular case of looking at a co-occurrence between two words. Let's say word I and word J. Now, in a sense, you can imagine that someone picked word I, and then another person picked J, and then somehow these choices gave a rise to how often they appear together, and that gave us A. So far we've been thinking about in the one direction, that is that we start from A, co-occurrence statistics, and then that has given a rise to these U and V matrices. But in fact, we could think about it from the other angle as well. At the end of the day, this is equality, right? We can always split it. Instead, you can imagine that someone chose, so I chose I and then J. So I wanted to know how often the word I and word J appear together. And then what happens is that the given I, somebody told me that, okay, this word has a disassociated vector. And then someone else, that person told me that, okay, given this J, word J, this J has disassociated vectors. And then we compute the dot product, and then given that dot product tells me what the Aij should be. So what is the count of I and J occurring together? So that's actually slightly different in the sense that we don't have to start with any kind of data to start with in this case. This is actually how we create a data. That's why we often call this as a generative story. That is that for each word in this document or the gigantic corpus we have, now how did we get that word? Perhaps how we got the word is that we start from the empty canvas, there's nothing, and then initially we are going to sample some vector, and then we sample yet another vector. And then the first vector is going to be our context vector. And then that tells me about what is the context of what we are about to write here. And then we're going to sample another vector, and then we look at the dot product. And then now I know that here's the context that I want to write about. And then which word should appear often. So if the sampled, let's say one vector that I sample is orthogonal to this context vector I have already sampled, then I know that the word that corresponds to this sampled vector shouldn't appear in this context. When I write it, that one shouldn't appear. I sample another word, another vector, and then if the dot product between these two are really, really high, I know that the word should appear a lot. So I should just type the word a lot, quite often in this context. So what that means is that you can imagine that now I have a document or the context embedding. So I'm going to start writing it here. So I'm going to say, some document embedding. I'm going to use V and then D. But the document can be just a context, right? The document is the one context that we define. It's going to be a D-dimensional vector. So we're going to draw or sample a document embedding vector that tells me about what should be written in this document. Document embedding. And then I'm going to draw a word vector, word embedding. And then what I can now know is that how often this word should appear in this document by looking at the dot product. So I sample what I want to write. So that's the document embedding. And then I'm going to sample which word I want to write. And then by looking at the dot product, I know how often I need to write that word. And then in fact, that's how we actually can create the whole document. I'm going to first draw what I want to write. And then given that what I want to write, I'm going to sample one word at a time, right? one vector at a time, trying to see how often I need to write it, and then I'm going to write it. So that's how a document can be generated. And then now let's put it a bit further by saying that in fact, there is a one more vector. Well, let's forget about it for now. What I want to know is that given this, what I really observe is going to be the probability of, let me see. I'll just rewrite it. It's a bit confusing. So I'm going to say that, okay, so with these two, I want to start writing a document. So when we write a document, what do? We write the first word, we write the second word, we write the third word, we write the fourth word, and on and on. So what I want is that once I sample this document embedding, and then I could sample all these word embeddings for all possible words you can imagine. Then the question I have is that for the ith location in the document, which words should appear? Should I write? This is a question. And then if I can tell that, I can suddenly just write the documents on the fly. And then one thing we know how to do is to define a distribution over all the words in the vocabulary. And then let's call it WI. So the word in the ith position given D can be written equals, I'll just call it W, given D equals, we use the softmax. And then how is the softmax or the score function comes about? The score function comes as the dot product between what I want to write overall, and then whether the particular word should show up in this document. And the compatibility, we're going to use the dot product. So VD transpose U. That was a pretty bad one. Okay, I'll just put it U there. UW over some, let's say W prime in V is going to be vocabulary. Next above BD transpose U W prime. So what this tells us is that, okay, so we are going to choose what should be written down. There is a document embedding, or that's the context embedding, right? So what should be written down in this context? So we throw BD, we have BD, and then given that one, I'm going to write one word at a time. Now, how do we do that? Is that I'm going to use a given set of word embeddings, or the word embeddings that I have sampled from, drawn from somewhere. And then given that one, I can now tell what should be the word in the ith location. And then I'm going to sample from it, write it, and then that's how I generate the document. Yes.
You might kind of generate maybe some nonsense, just like, because how do you take into account words you've already selected?
Indeed. So it's going to make a nonsense depending on how VE and UW are computed. At the moment, we are just assuming that we have a perfect VE and then perfect UW, and then this UW might as well encode about the information about the location as well. So you can imagine that this is a very simplified, high-level view of how we write. Is that there's something we want to write, that is the VD. So what is this document? And then for each of the locations, which word should show up, right? And then now you can imagine that this is in fact exactly what we already have done last week, studied last week. This is conditional language model. And what was the conditional language model? There was a language model that is telling us how to generate a document given what we want to write. In the case of machine translation, what was the thing that we want to write? Is what the source sentence meant. So what the source sentence meant, and then given that, now we try to figure out what is the word that needs to be used at each of the location in the translation. But what it tells us more generally, so beyond the conditional language model, is that the matrix factorization view there, what we did was that, okay, we know how often this word appears in this particular document, and then the number should be represented as a dot product of the document or the context vector embedding and the word embedding. And the other way to look at it is that if we know what should be written, and then what should be written is given to us as a context embedding, and then we try to look at what are the words or any kind of linguistic unit that should appear in order for us to be able to write the context or document. So it's back and forth. So it looks like we start from A, that is how the words already appear together, to extract the representations of the documents as well as the words. But on the other hand, it's the other way around in the sense that given what we want to write down, that is given as a PD, and then how each of these linguistic units are represented, there are going to be U matrices, U vectors. We can now draw how often these words need to appear for us to write a document that expresses the content that is given by this vector. And the nice thing is that once we have this kind of, let's say, view, then how we can estimate all these vectors and become a bit trivial, because how we do that? We're trying to maximize the log probability assigned to the actual document that we observe.
Yeah. So can we think of the earlier method as we need to use a whole corpus to find U and V, and the generative method as like we can do it incrementally with a little bit, and it becomes better and better as we add more corpus to it.
So the generative approach doesn't differ at all from what we learned. It's just how we think about the problem. Is that it's not that we make the observation first, and then the observation needs to be represented in a way that is convenient for us. But how we start is that we actually have this generative story or the generative model of what we're going to observe. We start from there, and then we make the observation, and then we try to figure out what have not been observed in that model. It's a subtle difference, but it's just a different perspective into the same problem. So let's just go back. If you look here, what this tells us is that we have co-occurrence statistics or the co-occurrence matrix A observed already. Now we're going to rewrite this A as a product of these two matrices. That's one way to look at it. But the other way to look at it is that any document is created by deciding on this document vector. So what's going to be written, and then for each of the locations, we're going to look at which word aligns most with this document vector that actually tells us what we want to write. And then we just sample from it, and then it becomes a document. That's our generative model. And then once we observe actual documents, so n subscript d many documents, now we can infer what were those document vectors as well as the word vectors. So in a sense, what this tells us is that when we do machine learning or statistics, it's impossible to not make any kind of assumption about our model. Because if we don't make any kind of assumption, the best strategy is to keep the data as it is and then present the entire data as it is. So when we think about what are missing information that we try to extract from this data, what we are saying is that we make some assumption about how data would have been created, we observe the data, and then we try to infer what are the missing bits. And then in this particular case of natural language processing or the document processing, the idea is that everything does not start from natural language or the text. Everything starts from these conceptual vectors. So the vector that tells us about what's going to be written in the document or in the context, and then the word embeddings. There are also conceptual, let's say, representation of each of the words. As I said, doesn't have to be document, right? It could very well be just contents. And then this context can change. So every location, this key might actually evolve as well. But this is just a one assumption we're making at the moment. is that for each document, we're going to have one concept vector drawn from some distribution, and then we're going to have the word embeddings drawn from some distributions. And how the document is created is by drawing one word at a time from this distribution that is parameterized using the dot product between these two vectors, or actually between many such vectors. And then once we have this generative storage and observe the actual data, actual documents that have been written, now then we can now try to infer back what those distributions are, or what the values of those vectors are. And then to solve that problem, we may actually run PCA under certain assumptions, which we're going to go through. So how does that actually sound like? The idea is a bit confusing. I totally understand. It has to be confusing a bit. If you took the deep learning course or the inference and representation course, it's a bit less confusing, but nevertheless, it is always confusing. Is that in order to, so let's say we're doing statistics, right, instead of machine learning. What is the goal of statistics? Is that you make some assumption on what kind of distribution or the generative process by which data was generated. And then you're trying to infer those missing variables that you don't observe. So those variables that are involved in the process of generating the data, but you only get to see the final outcome based data. Now then, can you infer those variables that you don't observe that were only involved in this process of generation? That's statistics. And machine learning turned out to be essentially the same thing. There are a few differences from here and there. The idea is that we need to make some assumptions about the process by which data was generated. And then often our assumption is that there was a highly nonlinear function that maps one particular data point into a certain distribution. Right? In our case, we always map it into the predicting some kind of conditional distribution. Right? And then we are trying to infer this process or the function that maps, that performs the mapping. Now, unlike in statistics, we don't really care about the particular value of those missing variables. We care about the function itself, whether we can recover the function. However, it's a similar thing. And what that means is that we need to make this assumption about how the data was generated. And then this is one particular way to do so. In this, the kind of, let's say, natural language processing. And then the nice thing is that once we do that, once we can infer these vectors, or we need to infer the distribution over vectors because there's always uncertainty. But let's say we infer the one particular point, let's say VD. Now that inferred vector tells us about what people were going to express in the documents that we observe. And then based on that one, we can tell whether two different documents are in fact similar with each other or not, which is not trivial at all to do so in the original text space, because of the issue of the sparsity as well as the lack of metric that makes sense. Yes.
This is something similar to what we did in the second lecture or so, but we just had one embedding instead of two. What's different in this environment?
In the second lecture.
Second or third? The classification.
That's actually the point. That's exactly the point. Is that it's exactly like classification, right?
But why do we have 2 matrices here when we make do with one?
Because the reason why there are 2 matrices or the 2 vectors here is because that's the assumption that we have made, is that the document is generated from the idea that needs to be expressed in this document and individual words that forms this document. In the case of classification, what was the assumption that we had? By the way, there were also 2 sets of vectors there. The input, the feature of the input, and the choice of the feature, choice of the input, and the choice of the class vector, right? So the samples that you draw are going to give a rise to which of the class this particular word of the text needs to belong to. So it's actually exactly the same. So there was the input vector, and class vector, or vice versa. So it's exactly the same, and that's the whole point. Is that these are all we all look at the same problem, but from a different angle, and then thereby we can come up with a different algorithms to solve this one problem that we solve.
So are these vectors as well learnable? It says that they are learning by different
We
methods.
are going to talk about what it means to learn. So, not clear what it means to learn, right? But of course, you can. If you minimize this, maximize this, the average slope probability assigned to the actual, let's say, observation of the documents with respect to, let's say, VD and UW, yes, we can. But we're going to talk a bit more about why we don't necessarily need to do so. We don't need to do so. But anyway, that's it. Let's think about just one more kind of, let's say, different generative model. The one nice thing about generative models is that once you decide on a model, a lot of things can be done automatically. However, unfortunate thing about generative model is that you have to make a decision on what is the generative model you assume. So as an example of how confusing the whole thing is, now let's imagine that this is a one generative model we thought about. Let's call it generative model A. I'm going to give you another generative model. Now here, the vector BD is not a real d-dimensional real value vector, but it's going to be a point in the d-1 dimensional simplex. So what does it mean for the BD to be on the d-1 dimensional simplex is that the values within this BD are all non-negative, and then they sum to 1. It's just like a tiny softmax or real value vector. Now, why is it d-1 dimensional? It is so we start from the d-dimensional vector, we apply softmax, and we end up with a point in the simplex d-1 dimensional simplex. The reason why we say this d-1 dimensional dimension is because we lose 1 degree of freedom, because we need to ensure that they all sum to 1. We can't really have an arbitrary, let's say, sum. Right? And then I'm going to say this BD is sampled from some Dirichlet distribution of some parameter beta, but beta can be anything. So the Dirichlet distribution is a distribution that is defined on a d-1 dimensional simplex. So I can say that, I'm going to sample this document vector, right? Document embedding that tells me about what needs to be written down from this simplex instead. And then I'm going to consider this as a mixture coefficient. So what do I mean by mixture coefficient is that I'm saying that there are d many topics that can be used to form that can be described in this document. And then this BD tells me what is the proportion, relative proportion of each of the topics. So perhaps I'm writing about I'm writing a news article. Let's say, what about a news article about one of the Major League Baseball team being sold to one of the, let's say, oil company or whatnot in the world. Then you can imagine that this article is about half sports, half business, and then perhaps 0 on all the other topics. Now you can imagine that this BD is telling me that it's 0.5 on sports, 0.49 on business, and all the other kind of, let's say, flat. So this is going to be BD. So this is going to be mixture coefficients or the topic proportion. And then what I'm going to say is that I'm going to ignore the actual order, but I'm going to ignore how it's written. Oops, I'm sorry. Just like above, I'm going to say that the probability of drawing a one word or the distribution over the word in the ith location, given this topic proportion, is let me see. Oops. Okay. Oh yeah, sorry about that. Sorry about that. And then what I'm going to do is I'm going to say that so I have the word embeddings, right? So this is U is going to be word embedding. UW, that's going to be usual word embedding. But then what I'm going to now have is the UT. And this is going to be topic embedding. So I have the word embedding and topic embedding. And then how many word embeddings do I have? As many as there are words in the vocabulary. How many topics we have? I'm going to have D topics. So for each of the topic, I have a topic embedding, and then I have D many topics, and this VD is the what are the relative portions of those topics to create a document. Then what I can do is I can write the probability of all the words within the topic. I'm going to say the length is T, and the document itself, so the choice of the document as the probability is going to be the sum for D prime going from 1 to D. I'm going to have the VD D prime. So this is going, so I'm going to look at the D prime dimension. So I'm going to look at each and every topic. I'm going to look at the relative portion there that's sliced out from the VD vector. And then for each topic, I look at D1 to T. So it should be product going from T1 to T, P of WT given V UD prime. Now what is this P of WT given UD prime? I don't know why I used the U. So what is this? I'm messing up too much. So hold on. Too many indices. Let's just call it K dimension. So then what is this one? This one is going to be softmax of X of W UWT transpose UD prime. And then it's sum over all possible words and then how they align with UD prime. So what is this? This part is exactly the same as before. So question?
Yeah, for the W1 to T, that's just like the words in your sequence.
Yeah. So this is the document that has been created. So this is the topic proportion, and then this is the document. So we're trying to look at the joint probability of the document, and then what should have been written.
So does D follow the direct distribution? Or-
Let's just write it even more specifically. We're going to like VE and then UD prime. All of it. So this is just a probability assigned to the topic proportion, and then the topic vectors, and all the actual words that we observe, and everything. So this is everything. And then what it says is that the given a topic, so let's say if the given topic was a D prime, then this is the probability that this word is selected for the position D. And then this is just like what we have looked at here in the option A, is that given what we want to write, that is BD, what is the probability of WI, so the W in the ith location. Right? So that's exactly what we wrote. However, that one is just for one particular topic. We can now have D many topics. So we can always move things around a bit. Here actually it makes much more sense to move things around. Sorry about that. Yeah. What we do is that we're going to look at each word, and then the probability of that word appearing is determined based not only on itself, but also on the proportion of the topic. So for instance, in this Major League Baseball example, if you have the word baseball, right, that baseball is going to be highly likely to appear under the topic of sports, but it's going to be very unlikely to appear under the topic of education. But then, so we are multiplying that with the proportion that is assigned, relative proportion assigned to those topics. And then what that means is that this one, we are now modeling the documents as the mixture of categorical distributions. Unlike before where it was just a categorical distribution. So this can be option B of generative story of how document is created. Now, obviously, you already know the option C. We can have an autoregressive model. In autoregressive model, what is our assumption is that if we actually don't have any global information, global variable that tells us about what the document should mean. But we're going to simply sample the first word, give them the first word, sample the second one, give them the first two words, sample the third one, and on and on. And then that could be yet another generative story. Now then the issue is, the difficult part here is that, okay, which one of these generative models makes sense? Which one should we use? Or perhaps you just notice that we're going to just replace some of these parts with the autoregressive model so we can make a mixture of autoregressive models. And definitely do that. Or perhaps you can replace a categorical distribution using the softmax with another function that gives us another way to get the categorical distribution. So how do we decide on which one of these generative models we should use?
I guess whichever one recreates the documents the best.
Good point. So whichever was the correct process by which document was created is what we want to use, except that we don't know. Because often documents are written by humans, and then figuring out how we actually tend to write text is the entire field of neuroscience, psychology, and natural language processing, so and linguistics as well. So probably not, that's the ideal criterion, probably not the most practical criterion. What else? How would you choose one? Of course, the best answer is that you just do exactly what I told you to do. That's almost always the answer. That's been the answer for a lot of the problems that I have solved over the past few years, but that's not really easy to do because my kind of, let's say, hourly rate for consulting is only going up. So I don't think you can afford it yet. Maybe in a few years, but probably not now. So there are actually two things that you need to consider. One is based on what you want to infer. So let's imagine that we train an autoregressive model. So our assumption was that the documents are generated one word at a time from left to right without any extra variables that tells us about the content of the document. That's great. But one thing that we don't get from autoregressive model is a single vector, single summary statistics of what the document is. That is very different from the case such as this very simple generative model, where under this generative model, given observation, we can infer for each of the documents what is the vector that represents the summary of the entire document. So if you wanted to actually get that vector that tells us about the entire document, then in fact, this A is probably the thing that we need to do, A or B. Right? In the case of B, what is the thing that we can get? Is that we're not going to only get the document vector itself, but we're actually going to get, for given documents, what is the relative proportions of these topics. And then maybe that's important. In that case, B has to be used. And then again, C is not going to give you that information. Autoregressive model is not the right generative model to use if our goal is to get some kind of summary statistics of the documents. Right? Okay, so what you need to estimate has to be part of this generative model for that generative model to be useful. Now, what would be the second criterion? Second criterion turned out to be how well this generative model fit the actual data, right? And then that actually goes back to the idea of, okay, it has to be the correct generative model by which data was created. Now we cannot check the correctness. It's impossible. If we could check the correctness and then we can get the correctness generative model, then we wouldn't do machine learning, we would just use that process as it is, right? So instead, what we can do is that we go all the way back to what we talked about earlier at the very beginning, is that we use the validation. Now, a lot of the Bayesian statistics or the Bayesian machine learning people are going to just freak out by hearing about the validation, but that's okay. They all use when they have to actually solve problems, the validation. They just don't tell people that they use it. Well, obviously, this kind of validation can also be put in the context of this kind of generative model. Is that at the end of the day, with this kind of generative modeling, what we have is the actual observation. So we're going into the probability modeling of it. What we have are two things. One is that we have the observation. And I'm going to a bit zoom out, and I'm not going to talk about the natural language at this point. We have some observations. This X is a random variable that represents everything that we observe for each and every example. And then we have some hidden variables. And I'm going to use Z to say that it's a hidden variable. And then we have the parameters. And I'm going to use theta. And in probability modeling, all these are random variables. And then what that means is that we have the associated probabilities. And then what are these associated probabilities is the probability of observing some data point, let's say document, given some hidden variables, and the parameters. And then what are these hidden variables and parameters? You can imagine that this is going to be a document vector, document embedding, and these parameters can be word embedding. And then this X is the actual words that we observe in the document. And to complete this, what we need a prior distribution. So if you don't have any idea, or if you don't see any data, what is the reasonable distribution from which the document embedding is sampled? What is the reasonable distribution over which the word embedding is sampled? We haven't seen the data, but we need to use some kind of prior knowledge. This can be very simple as just a standard Gaussian distribution. But these are the things that we're going to define. And then this is what the generative model is. And then this is what ABC actually told us about. In the very first one, Z was the document embedding DE. Theta consists of all those word embeddings. And then this P of X given Z and theta was the distribution over the words given the document embedding and the word embedding. And then the same thing in the case of the B, option B, the mixture of categoricals. In that case, now we have Z that was the topic proportion. And then theta had two sets of embeddings. The first set, the word embeddings as usual. Second set, the topic embeddings. And then this distribution was back for each word, given the document, the topic proportion and all the other parameters, was a mixture of categorical distributions. And then in the case of the autoregressive model, Z was nothing. We didn't have Z. We had theta that is a neural net parameters. And then P of X given theta was rewritten in an autoregressive way. And then we were able to compute them. That process can be a bit extended. So by saying that the learning, so this is where the learning comes from. Learning in this case can be thought of as trying to compute the probability of theta given X, or let's put it not X, but training data. At the end of the day, what we want to know is that if we know the distribution over theta without looking at the data, we know, given this theta as well as the Z, what the data should look like. Now then the question is, under that generative model, once I observe these data points, training data points, what should be the distribution over this field? So this is the prior likelihood, and this is often referred to as posterior distribution. Now, once I see the data, what should this theta be? Now, of course, you can imagine having a similar thing. Once I observe this data, what should those associated, let's say, the train, ZB, right? So the latent variables, hidden variables. And then we can imagine that if we're trying to infer the distribution over this theta, given what we have seen. And then that's going to be learning. And then if you think about this from the learning perspective, then what you want, in fact here, let me actually rewrite, instead of this P, I'm going to use Q here. Now, one thing I want to point out is that the P that we often use to refer to probability, density, or mass, is the most overloaded symbol in the history of mathematics. So whenever I use P here, you have to always look at what are the variables that we're computing that over. But then you also have to be mindful about what are the variables we are conditioning the whole thing on. Because P of theta and then P of theta given D train, these two are completely different things. So let's use Q for now in this case. Now you can imagine that because the observations are all conditioned only on the parameters and the latent variables. Now you can imagine that what can we do? How good is our learning procedure? That can be computed as computing the X test. So I'm going to take one test case, given some theta and Z, but then this theta and Z are not going to follow the prior distribution, but they are going to follow the posterior distribution given the training data. Then we can consider all possible combinations under this posterior distribution. And then this ends up being X test given the training. And this is what we call predictive distribution. Oh, yeah, of course. Should be Q. And then what this actually tells us is that if we can somehow guess this posterior distribution, so what we believe theta and Z be given our observed training data, then based on that, we should be able to compute this predictive distribution and how likely this test set is. And then this whole thing is in fact a function of our choice of the conditional distributions and prior distributions. And then that's why we can use this predictive distribution in order to essentially compute the low probabilities. Our model, our choice of the generative model is going to be assigned to the validation set. And that is going to the second criterion by which we can actually choose which generative model is better. Because some generative models that more closely match the true generative process by which the data was created and for which we can do this posterior inference will have a better predictive capability on the new data points. And then the new data points is just a validation examples in our case. So those are the two criteria we can use to choose which generative model we use. It turned out that we can't be too crazy about generative models. Now, if you're working in statistics or economics, we should be crazy about generative models because generative models respond to your own theories of how work works. And then your goal is to figure out how to infer all these values and then show that it actually has a very high predictive power. And then it actually recovers some of the properties that we know exist in the world. Now, in the case of machine learning, we are solving problems where the theories, we don't even have theories. We don't know how to solve it. So in a sense that our goal is to make as simply generative model as possible, and then trying to maximize this predictive probability or the predictive power. So next week, of course, I was able to cover only half of what I planned to cover. But next week, we're going to just speed up because I saw that there were some midterm course evaluation feedback saying that I'm teaching too fast. So we're going to push it to the extreme next week to cover what we really want to cover everything for this semester. I'll see you all next week then.